Hello and welcome to Manifolds, a video series I started for everyone who wants to learn how to use calculus on surfaces and related topics. However, before we start, I really want to thank all the nice people who support this channel on Steady, via PayPal or by other means. Now, in part 1 of the course, I give you a short overview and explain the definition of a topology. So let's start with a quick explanation what we will discuss in this course. First, as I've already mentioned, the notion of a manifold generalizes the concept of a surface in space. Such a surface we could visualize like this, but the most popular one would be the two-dimensional sphere. So this is the boundary of the ball and often called S2. The 2 stands for the 2 dimensions we have when we just live on the surface. Now, you might already know some important applications where it is needed to calculate on the sphere. Especially in physics, it happens that some constraints force the motion to happen on the surface. Then, questions like finding a minimum or a maximum of a function are completely different because we can't use our calculus for open domains anymore. Therefore, the overall question here will be how to extend our calculation rules for surfaces and indeed abstract manifolds. In order to do this, we first have to understand what the fundamentals of such a surface are. So, we start with a quick overview of the field of topology. Afterwards, we will be able to define differentiable manifolds as our subject of study. So you see, the notion of differentiability will be a crucial point in this course. Then next, for these differentiable manifolds, we will be able to define so-called differential forms. At first glance, these differential forms might look strange because they are just given by one part of an integral like dx or d omega. However, we will define these objects in a rigorous way. And indeed, in the end, also integrals with these differential forms will make sense. Okay, now the overall goal I have in mind for this course here is that we will reach the generalized Stokes' theorem. Indeed, this theorem will nicely form a connection between a manifold and its boundary by using differential forms. So, this is the overview of the course, and I think we are ready to start with the first part and talk about topology. Now, if you already have a good knowledge of metric spaces, you can use this as a starting point. Indeed, a lot of notions we have in topology are already formulated in metric spaces. Here, please recall, a metric space needs a set X and a distance function d. This means when we have the set X, we can measure distances between 2 points in X. For example here, X and Y have a distance given by a positive real number. And this one is denoted by dxy. Now, in the case you see this the first time, you can watch the first videos in my functional analysis course to get familiar with metric spaces. However, the important thing here is that you know how we can define open sets. Usually this works when we take so-called open epsilon balls. This means that B epsilon x is a ball with radius epsilon and middle point x. Now by using these epsilon balls, we can say if a subset in the metric space is open. Hence here, the notion open for a subset depends on the chosen metric D. But then we can show that the collection of all open sets fulfills some nice properties. For example, if we take 2 open sets, the intersection is always also an open set. With such properties in mind, we see that for a lot of things we do not need an explicit measure of distance. Just some neighborhood relation between the points might be sufficient. So roughly speaking, we just need to know which points are neighbors of x, are close to x, without measuring the explicit distance. Indeed, the abstraction of this idea leads to topology. Hence, we just list all the sets that should be open and then we deduce everything from them. Most importantly, in this definition we don't need a metric anymore. However, of course, we still have a set X. Then what we need is the collection of all subsets of X, which we call the power set of X and denote by P of X. Therefore, to say which sets are open, we just have to take a subset of the power set. And this one is denoted by a curved T. In other words, this T just stands for a collection of subsets of X. Now, these subsets should be the open sets, therefore they have to fulfill all the rules like in the metric space. Indeed, we will fix 3 important properties here. Now, the first one is very simple. We just say that the empty set and the whole space X are open sets. More precisely, they are elements of the collection T. Then, the second property I already mentioned, if we take 2 open sets A and B, then this implies that the intersection is also an open set. Finally, the third and last property looks similarly, but now for the union. However, you might know, in a metric space with the union and open sets we can do a lot. What I mean is, it does not matter how many open sets are in the union. The result is always an open set as well. Hence, here we can look at a whole family of open sets. So we look at AI, where I goes through any fixed index set capital I. And of course, any subset in the family is an element of T. And then this implies that we can look at the big union I in I of the sets AI, and we conclude this union is also an element in T. Okay, and there you see, we condense the properties of open sets for a metric space into a new definition. Indeed, with this definition we can work and we don't need a metric anymore. What we now have is a collection of subsets T, and we call it a topology on X. And I already mentioned it a lot, the elements of a topology are called open sets. Therefore, please always remember, in a topology, the property open is given by definition. And therefore, open only makes sense with respect to a chosen topology. Okay, I think it will be very helpful when we look at some examples. Therefore, let's start with the easiest examples. So the question is, what is the simplest choice for T such that all the rules are fulfilled? Of course, in order to satisfy the first rule, we need at least the empty set and X involved. However, if we leave it at that, we already have a topology. So what you should see is, the second and the third property are immediately satisfied. Simply because there are not many choices for the intersection and the union. Hence, this means that this is the topology where all the non-trivial subsets are not open. So maybe not the most interesting topology to work with. Okay, now you might already know, we can also do the other extreme. Which means we have the topology where all the subsets are open. Of course, the power set of X is a topology on X because there's no way to violate one of these rules. The power set just contains all the subsets. And now in this topology, all these subsets are open sets. Therefore, we often call it the discrete topology. On the other hand, the first example is often called the indiscrete topology. Of course, both examples are not the most interesting topologies, but they are edge cases you should always have in mind. Okay, maybe that's good enough for the introduction today. Let's continue in the next video while working with the open sets. Therefore, I hope I see you there and have a nice day. Bye.